Hello, everyone, and welcome to our WEkEO workshop monitoring cryosphere changes. Welcome to our practical session. My name is Andrea Carvalho. I'm a training officer at Mercator Ocean International, and I'll be your host for today. Just a few guidelines before we start. We are on Zoom for this session. You can use the Zoom chat for small talk or for any technical issues you might have. But if you have any sort of questions related to the workshop, please use Slido. We will share the link in the chat as well with you so that you can go there. Besides using the link to Slido, you can also go to slido.com and use this code you see on the screen now. You will go to our session. Just some more information about this whole workshop. The recordings will be put on YouTube, on our YouTube channel, WEkEO DIS. There you will also find previous workshops we've done. Please go there if you want to learn a bit more about WEkEO and also watch these sessions again. Also, the same presentations we presented yesterday. We had two very interesting speakers with us, showing us very interesting use cases of how to use WEkEO data in their professional activity. We will also make these presentations available. So you will receive an email with all the useful resources. And for today, as I said, it's a practical session. So if you want to follow along the tutorials we will be showing today, please download these resources we are showing here on the slide. We will share these links in the chat as well. So that will take a few seconds for you to have these tutorials. But we recommend you to do this if you're already someone experienced who has already used QGIS and Jupyter notebooks. If not, just sit back, relax, and watch our sessions. So today we will have three very nice presenters. They will do. We will have Alexandre Boris, who's going to do a demonstration of the WEkEO viewer. He will show you how to visualize WEkEO data and how to download it. Then we will have Daria Andreevskaya from Novelties, who's gonna show us a very interesting QGIS tutorial on how to study the dynamics of glacier ice, especially the glaciers in the Alps. And after a short 10-minute break, we will have Alexandre Meran, also from Novelties, who's going to show us how to study the dynamics of Antarctic ice shelf using Jupyter Notebook. If you want to follow these sessions independently, because today might be a little bit long, you can connect at these times that you see here. And that's it for me. I will give the floor to our first speaker of the day, Alexandre Boris.
Hello, everyone.
Hello. So whenever you want.
Okay, thank you. So I'm Alexandre Boris from the WEkEO user support. And today we will see and talk about the WEkEO data viewer. We will see how to download and visualize data. And we will see the WEkEO data viewer to familiarize yourself with the WEkEO data viewer. So first, let's meet on the WEkEO homepage. This is accessible via the URL wekeo.eu. First of all, we'll see how to register. So
sorry,
to register,
Alexandre,
yeah.
You're not sharing your screen?
Oh, sorry.
I don't know if you were. Yeah.
Yeah.
No worries.
That's it. So
perfect.
The WEkEO homepage. This is accessible via the wekeo.eu URL. First, let's see how to register. So to register, it's free, totally free. This will give you access to download the data and to have access to many tools. So you just have to fill in the form and create your account. Now you can access to the WEkEO data viewer via the data button, like this. See, if it's the first time you going on this page, you will have two layers display on the map. if you want to search for another dataset, you can click on the plus button. Here you have access to our catalog. On the left, you have all the filters with a search box at the top if you want to enter some keywords or completely the name of the dataset. You have filters like the Copernicus services, the platforms, the area, many tags, and on the right, the dataset available with many informations. So today we will choose a land dataset with the tag vegetation, and we will choose the vegetation phenology and productivity, which is a yearly dataset. So here's his title. You can see that 28 layers are accessible and viewable on the data viewer. On the left, you have a thumbnail, which show you how the data will be displayed on the map, and a quick description of the dataset. So we click on details to have more information. For some dataset, there is some use cases where you can have a quick example of what you can do with this dataset. You can see also the thumbnails we see before. You have the geographical extent of the dataset, an abstract, which is more detailed than the one we see before. You can have access to some information like the dataset ID, the Copernicus service, the area, and you can have access to the metadata of the dataset. So let's add this layer to the map. We will have to choose a variable we want to display. So today, sorry, you can see it. We will choose the total productivity variable, season 1. We click on add to map, and we can see that the layer is displayed on the left. So let's click here. So we have his name, his title, the date of the data display on the map, the hour, the area, also the color map of the data display. So if you want to zoom in or zoom out on the map, you can use your scroll mouse like this, zoom in, zoom out. You have the time scale at the bottom of the page where you can choose a date. Here we have a yearly dataset, so you have to choose 1 year between each date. For some dataset, like the seawater velocity here, we have a depth scale, so we can change the depth to update the data. You have this orange icon to show or not the data on the map. Like for example, if I want to remove the seawater velocity icon like this. Then we have the locate tool to place a point on the map and see his coordinates. We have the measure tool to measure the distance between 2 points. Quick tip, if you want to only draw 2 points, you can press escape to quit the tool like this. And then one tool which is important is the set AOI tool to draw a bounding box of the data we want to download. So for example, I will draw a bounding box in the water like this to subset after. And now we will talk about these few buttons on the seawater velocity dataset. The first button is the download button. So to download, as I said before, you will need to create a WEkEO account. So it's free, just you have to sign in and you will be connected. There you have access to the parameters of the download. So we will see this just right after. The show layer information. So this brings back us to this page where we have all the information on the dataset. The layer button to change the variable we want to display on the map. So this allows you not to go back in the catalog, search for dataset, and change the variable. You have direct access with this button. Then we have the parameter button to change, for example, the opacity. This can be useful if you want to cross the data with two data sets and compare them directly on the map. And then you can change the color map. You have many choices. So just change the color like this. You have the log button to change the color map into log scale, like this. And we have the vector button to display the vectors of the layer. The resolution adapt with the zoom we apply. And let's see now how to subset your download. So you can enter a bounding box manually by entering the 4 coordinates of the bounding box, but you can also copy your AOI we drew before from the map like this. This will automatically enter the coordinates of the bounding box. And you can subset your data with date, start and end date. Also, you can enter it manually, or you can choose a date from the calendar with the calendar icon, or you can copy from the layer the date with the time scale at the bottom. So let's choose, for example, January, and another date not far away, like this. So we'll download like 5 days for this data set, and we will choose for today all the variables. Why not? Here is two buttons, so you can show the API request. This is something that you will use if you want to download data via script. To download data via script, you can use our HDI API client. Here is our article to show you how to do this. You have some commands to run your download. But this can be also useful if you encounter some problems with the download or the dataset. You can share this API request with us in the chat we received just before, just after. So we can search with you the source of the problem. So this is API request, and now we can request the data to download it via the WEkEO data viewer. So the request is now completed, but you see that it is running for like few seconds. It depends on the date and the bounding box you choose before. So you have the button to display the API requests of your request, and the folder icon to orders all the item you want to download. So for this request, we have 5 items. You can click on order to download it. Here we have around 2 GB of data. So it will take a few seconds or minutes, depends. But I did it yesterday, so we have this icon to download your data. You can click on it, and this will allow you to download your data directly on your computer. If you have many items and you don't want to order them all manually, as I said, you can use the HDI API client to download in few command lines all the data, all the items in just one line. So if you wish to download more items in a quick time, you can use it. If you encounter some problems, you can contact us via the WEkEO widget at the bottom right. Here is not, but if you don't see it, you can go on the home page and click on it, go on message and send us a message, and I will be glad to answer any of your questions. So thank you for listening me, and if you have any questions, let me know.
Thank you, Alexandre.
You're welcome.
We do have 2 questions.
Yeah.
Let's take a look at the slide here. First one, can we upload our own AY shapefile?
Not actually. If it's a bounding box, yeah, you can select your coordinates on the bounding box, but we are working on a tool to allow you to upload a shapefile and download only the data you want. So not actually.
Ready. And second one, can you share the link to the HDA API Python guide?
Yeah, I will do something. If I can share my screen.
Yeah, sure.
Yeah.
We can stop sharing Slido maybe for a second and thanks.
Yeah, thank you. Up, share. So on the homepage of the WEkEO, you will have the support button, and you can click on Help Center. And by searching for HDA API client, you will see this article, how to use it. And in this article, you will have all the information you want, such as how to download and install the HDA API client.
Okay. So all the resources are pretty much online. Just have to know
in
what
the
to
Help
look for.
Center, if you have other questions, I think you have
a lot of the
you'll
answers
find
already.
yeah.
Great. Thanks a lot, Alexandra. That was very
You're
nice.
welcome.
And now we can already jump to our next presentation. That will be Daria Andreevskaya. It's gonna show you how to study the dynamics of glacier ice in the Alps.
Yes.
Good.
Yes.
Okay.
Hello.
Floor is yours.
Yeah, you see me, you hear me. Everything's
Perfect.
good. Yep.
Mhm.
I'm gonna show my screen. Okie dokie.
That's great.
You see my screen?
Mhm.
Yeah, great. Okay, so hello everyone. My name is Daria and I'm from Novelties. I work here as a scientific engineer. And today I'm here to show you how to use QGIS software in order to use some products from WEkEO Copernicus DS service platform. So today's topic is Cryosphere, as you might already know. And we're gonna look at fluctuation of the Aletsch Glacier, which is the largest glacier in the Alps and is situated in Switzerland. And for example, here you can see a little not so happy, not so pretty image of how this big glacier reduced in well, quite a lot of times, like 150 years basically, but which is still not a good sign for us and for our planet. So yeah, the glacier is basically the highly compressed ice and snow, which is accumulated either on poles regions or in mountain regions. And this is a very important source of water, of fresh water to the nature, to the animals, and sometimes also to the people who live just around, like below, and so on. And yeah, we're gonna look at the evolution, the fluctuations of this specific glacier in the Alps. So I'll go directly to the QGIS. QGIS. I hope you still see my screen and you see my QGIS and not my presentation.
Exactly.
Okay, great. So we start from a blank screen. Basically, you create a new project, and first thing what we're gonna do is we're gonna have some projection to see what's happening around, like the map. So for this, we go to layer, we add layer, and we choose add XYZ layer. And here it will, well, if it's your first time at QGIS, it's going to be nothing here. So you can click on edit here and add new one. So you can add whatever name you want and put an URL. This is a URL for Google Satellite Hybrid because it has, well, nice picture. We can see basically everything what's happening, like with all the cities and stuff, quite high resolution. So the same what you see in the Google Maps when you activate satellite mode. And this, if you want this link, it's going to be like all the links and all more precise tutorial step by step is also going to be provided to you in a Word or PDF file, or already provided, I don't know. So we click on load add, and it did add. Well, you don't look at it. This is not for you to see. It's just for me. I'm going to remove one. So now we have the whole map, how we see it, how like Google Maps shows us, and we're going to zoom to the Alps. So here, what we're going to do, we're going to work with two products from WEkEO service. And as Alexander already showed you how to download, I'm not going to show you how to download it. I'm just going to show you which ones we are using. We are using the Copernicus High Resolution Snow and Ice Monitoring Persistent Snow Area. So it's basically the areas that always, like through the year, covered with snow. And the second one here is R5 monthly average data, which we're going to use for the meteorological data. And yeah, in WEkEO, for example, you cannot see R5, but persistent snow area you can if you really zoom in, and it will take some time to load, and also depends on the date. I'm not going to spend time here. Okay, it's here. Also, what we're going to use for our tutorial is the plugin. I don't see, unfortunately, because yeah, okay. Plugin for QGIS. This is a plugin which Novelty's developed to facilitate the importing NetCDF files, because NetCDF file is this file with like nested variables, and QGIS by itself sometimes might misunderstand some information in the NetCDF files, and or it's just not very practical. So there's a specific plugin. You can download it here. I guess you will. I mean, this link you can see it in a document format of this tutorial, but I think it's also going to be provided to you maybe in a chat or something. So we go back to our QGIS, and first, what we're gonna do, we're gonna work first with satellite data, so with satellite images, and this was this what I mentioned before, persistent snow area product, which is derived from Sentinel-2 images. It has special resolution of 20 meters per 20 meters, and basically it consists of tiles, so a tile which covering like some specific region. And we're gonna look at more or less this kind of region, which like covers the some part of French Alps, Italian Alps, and Swiss Alps here, because in this area we have the biggest, the largest glaciers in the Alps. But we're also gonna focus on the one specific one. Is here. You see also like with this layer in QGIS, you have a very nice resolution. You like literally can see the snow like this, or crevasse and stuff like this. So that's quite useful. So moving to the data. So the data is also provided to you. And what we're gonna do, like here, we are choosing this persistent snow area. And previously, I prepared all the data specifically. So like you of course can like go to WEkEO and download more data if you want, like whatever. But I already prepared the data. So there's data for 6 years from 2017 to 2022, which is quite a lot. We're not going to look at all of it. I think I'll stop on like 2 or 3 years, so just to see some evolution, but not too much because it really takes time. And you guys can do more or less, whatever you want. And for each year, we have satellite images. So from some date in May. So we decided to take May because from January to May, we assume that it's the most active. It's a like time of active accumulation of snow for glacier. When it's snowing, it's raining, depending on the weather, and so on. And at May, it slowly like starts from, well, we know what we don't ski in May, right? So we will assume that from this it starts to melt. So we also assume that, well, you can see, for example, that there's like 10 days difference between these images. We assume that there's not going to be not big difference between these images. So what we're going to do, we're going to start with 2017 year and to start putting our tiles. First, how we can, this is TIFF image, TIFF file. So we can either just select all our stuff and like drag and drop it to our QGIS like this. It's nice and oh, of course it doesn't see it because I'm gonna do this. So it looks like this. So we chose only 4 tiles. Here this is this persistent snow area, which in black it means, well, there's no snow. White it means very snow, which is already nice. We can see some outlines. And also, if you want to know how to, we also can add layers differently by just clicking on layer, add layer, and as it's TIFF, it's a raster layer. And here you can just browse to your data, click to the data and choose it like all of them and add. So here we have it. I will work with this layer only. So like with this date, with this year only. And I already prepared the other years before. So I'm gonna just then show you how to compare them, but we're gonna work like with only one layer. So it's like with only one date, so it's faster. So what do we have now? We imported our images and we can even, for example, we can add a group and call it 2017 and we move them also. It's gonna be a bit up. Yep, like this. So now we have our tiles and we're gonna work with it. So first what we're gonna do, we're gonna merge these tiles because we see that we, for example, can untick the box. So it's not exactly one image, it's 4 different images. So we're gonna merge it. For this, we go to toolbox. The toolbox is usually here, but it might be not be here if you just open a QGIS first time. It's represented as a little gear, which I don't see because Zoom covers it for me, but it should be somewhere here. It's written toolbox if you click on it. So what we go to merge function. We can just search for it, merge, and we need this one function. We click on it, and here we choose input layers. So we are choosing, I assume this, wait, I have a lot of them, of course, because I already did it before, but so we choose these 4 layers. I think then, no, well, was it 17? Yeah, it is 17. Oh, it's the same one. Okay. I think, yes, this is TLR, TLS, TMR, and we need also TMS, this one, right? We click on OK. We choose the output as int 32 or int 16 because we know that it's only 0 or 1s. And we can save it to some file. I'm not going to save it. Well, you guys probably do. And well, I already saved it before, so we'll let it run. Hope it's not going to take too much time though, because sometimes it does. I guess, yep. So now we have a merged one. We're gonna click it on, we're gonna okay, so now we have our merged one for 2017. Great. So basically, if we look, I prepared it for you already. We have a merged one for 2018, for example. No, it's not this one, sorry. No, it's this one. It's already, yeah. Yep. We have for our years and we're gonna compare them later. So far, we just gonna focus on our our 2017. So, yep. So now we have this, it's a raster layer, so we cannot kind of do much with it. So what we want to do, we want to make it a vector layer to perform the next calculations. So first we gonna polygonize it. For this we go to raster layer, conversion, polygonize. We choose our merged. Here it's a name of our variable. Also, we can save it or not, and we run it. It can take some time because if it's a lot of pixels, high resolution, it can take time. So as soon as we polygonize, so now basically our our raster layer, instead of like pixels by pixels, represented by small polygons which are replacing the pixels. And we're gonna then filter it, so we see only the snow and don't see this black stuff which doesn't have snow in it. Okay, it finished. We're gonna do like this. So now you see, I mean, that's all this is a lot of polygons. And to filter it, we're gonna right click, there's filter. And to filter it, we're gonna put this PCA equal to 1, I believe, because 1 represents the snow. Yes, it tells us that it's chose only some rows. Okay, we click OK, and now we zoom, and we see, for example, that here we see that there's a snow cover. Okay, so we're gonna move to our glacier, to the Aletsch glacier. It's this one exactly. Like if I unclick, you see this is the Aletsch glacier here. It consists of several others, but we don't really care about it right now. And here, we see the glacier, the snow cover, and so on. If you want to find you will have a file, so you can just always zoom to layer and to, now it's not going to be zoomed exactly to Aletsch glacier, but it's written how to find it, so should be okay. So what now? What we're gonna do next is we're gonna look how is it. Well, we can also look at the evaluation of it because I already did it before, so not to lose time. But also, like here, for example, we have a Google Maps photo, and we see that there is actually snow here, right? I mean, we clearly see it, but our persistent snow area variable doesn't really see it. So the problem might be in the thing that, for example, the glacier, when it moves, it also drags with itself a lot of different debris like sediment, sand, rocks. And of course, from the satellite point of view, this is not snow anymore. So, which means that basically, of course, we can use this specific snow cover variable and many others that are presented from satellite data. But that's not exactly the only tool that we should use, because there should be some complementary rules. And to see that it is kind of true, we will look at some external layers. So now we will learn how to add external layers and work with them. And this external layer is being provided by, I don't see it again. Okay, so this is been a glacier inventory of the Alps from Sentinel-2. So that was a little, let's say, mission where when different researchers studied the evolution of glaciers in the Alps by comparing not only satellite data, but also like having in-situ data by going there, literally measuring where the glacier ends and so on. And this data, we have it also in our data folder that's called Glacier Inventory of the Alps from Sentinel-2, and it's presented as a shapefile. So here we need this one. It's a shape CHP or CHX. What is it? Format. Sorry. So we again can just drop it like this, or we also can add it from add layer. But now we would need to add vector layer because shapefile is a polygon. It's a vector. It's not a raster. So I already added it. I assumed. Okay, the color is kind of the same. Yeah, you can change the color by double clicking, going to symbology and choose whatever you want. Like I'll choose, I don't know, green, so it's more visible. Okay. So now, yeah, this one is basically the glacier, how glacier looked like in 2018, because the article was from 2018. And you see that they combined different methods to calculate the area. And if I do this, yeah, you see the difference that here we will, with our snow, persistent snow area, we lost it. And again, like, yeah, persistent snow area. So it's, yeah, as I said, it like the satellite takes a photo, it might not capture it if the snow is covered, like if snow is not super clean and with stones and stuff like this and rocks. So yeah, like this, we see it. But even though we see that we need more tools to do that, to like make a more like profound study of this subject, we're still going to continue because, well, this tutorial is also about how to work with different data in QGIS. So we're going to continue exploring different functions. So what we're going to do, what we want to do is to calculate the area of the glacier, like how did it change through the years. And for this, we're not going to use the our this external layer. We use what we obtained. But here, the first thing that we need to do, that's not a glacier, that's not the exactly LH glacier. So we need to crop our data. So for this, we will create a polygon. We go to layer, and now we do create layer. So add layer is something that already exists. Create layer if you need to do it from scratch. We go to, we choose new shapefile layer because it's going to be polygon. We choose geometry time as polygon and file name. Well, I already have it, but whatever, I put it area 1, for example. And okay, so now we have a new layer appeared here, but well, there's nothing here because it's empty. So to edit, we click on it and we toggle editing mode by this little, I assume it's a pencil. Okay, so now you see that pencil appeared here. We can change it. We see that some options are now available to us. And we're gonna click on here at polygon feature. So we're gonna basically draw our polygon. So we know that the LH Glacier starts from this Concordia Plus or something like this, when all the glacier joins together. So we're gonna start drawing. So we choose different points and we basically trace our glacier. Yeah, I don't know how far it can go, so let's say it's here, 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 and here. So now we have a polygon. We right click on it, and well, now it gives you like number of feature, but it's whatever. Great. So now we have something like this. That's a polygon we just created, right? So to cover the area, and we're gonna exit the editing mode. It will ask to save it. We say yes, we want it to save. So now what we're gonna do, we're gonna clip this polygon, the huge polygon with a lot of with different glaciers with different area. We're gonna clip it by this, basically a mask I just created. So for this we go to vector, I think. Yeah, we can go to here, but yeah. Okay, so vector, yeah, actually some of the functions here, like in a toolbox, they are repeating here. So that's, again, like depends on how you like it. In the geoprocessing tools, we have a clip, yeah, this one. So we use input layer, so the ones that we want to have like our data extracted. So it's our vectorized, there's it here. And overlay layer is our mask, so it's area 1. We can also save it. I'm not gonna save it. Okay, that's actually nice that we have it. So first, we see that this error appears. It has that vectorize has invalid geometry. That happens very often. Then you polygonize from raster to vector layer, and that's just QGIS thing. So before we move to any other things to do to any other steps, what we need to do, we need to fix our geometry. So for this, we go to fix geometry, not that buffer, fix geometries. And we choose our vectorized. We can again save, we run it, it'll take some time. So basically there are some instabilities, there are some like polygons that are closed, not closed because of this polygonize function. So yeah, it might not, like what you see, it seems like it's okay, but apparently it's not. So we need to like clean the geometry. So now we have fixed geometry. It's now orange, right? Yeah, okay. No. Okay, so now we can do the clip stuff that I told you before. Vector, geoprocessing tools, clip. So it's fixed geometries and overlay, it's area 1. Okay, great. So we untick our area. So now we have our clipped area, you see? So now only this is our LH glacier, so nothing else. And like this, we can proceed with others, like with our years, we will do it. I'll show you how to do it. And now if you can click on right click on our layer and go to attribute table. You can see that actually that's a lot of different polygons, which like you can see that there's some small points and stuff. You also, I don't know if it will be represented, you can flash the feature. Well, I guess it's a small flash feature, very small feature, we don't see it. Yeah, okay, so you can like really see it, but now we see that it's several polygons. So if you want to calculate area, it's going to be quite not real nice because it's going to calculate area of each small little piece of this polygon. So first what we do, we're going to dissolve it. So have one big polygon consisting of all these small ones. For this, we can go to vector, geoprocessing tools, and we have dissolve. So we have our clipped, dissolve fields, optional, that's all optional, so we're not going to use it. And we're going to run, close, and we have now dissolved, which is the same, but if we right click and open the attribute table, we see that it's 1. Great. So now what we do, we're gonna we're gonna compute the area. And to compute the area, we can do different ways. First, for example, if you just want to know the area, but just for yourself, or like to compare with some other tool, you can always go to, okay, thank you, Zoom. So this little icon, it's called identify features. We click on it and we click on our feature. Here it has like clipped and dissolved. So we're going to use dissolved. And here I can go back. You see, we clicked on it and we have some data which QGIS already knows about this feature, this data. And here we see that, well, in actions, we have nothing because we didn't perform any actions in, but in derived, it gives you coordinates, it gives you area, gives you perimeter, also like a lot of information. So you can see the area in square meters here, right? So if it's you just need to know this data, like, you're not going to use it further, or like to use it further, but not like in QGIS. But if you want to know, let me go back, okay. But if you want to have it like really calculated and saved somewhere in QGIS, what we're going to do is we highlight our layer, go to editing mode again, and now we right click on it. We go to properties, and next it should be fields. No, okay, fields. And there is this little field calculator. When we click on it, we can have lots of different functions we can perform on the data, which is stored in the attribute table, which we saw before, and like also with geometry itself. So we're gonna create, I guess, a virtual field. Yeah, okay. So here we're gonna put this formula. I'm just gonna put it, copy pasted, but it's basically an area. You see, if here you can search for area, and it gives you different there are two. There's also like, that's a recent one formula. So this one we want in kilometer square. Yes, and we choose it as a virtual field, I think. Yes, we've put a field name, so it's area in kilometers, and we want, yeah, like double and, oh no, wait. Yeah, we want double, right? Yeah, okay, we cannot choose, okay. So, yep, we click on OK. We also actually already see a preview here, and we can click on OK, just apply, just to verify everything is good, and OK. As soon as it's done, we of course like untoggle it, great. And in attribute table, we open it, and now we see area in kilometers. So this information you can actually, like, you have it in QGIS for later, and you also can export this data for later, for example. Okay, so this is done, and now what we're gonna check, I guess we're gonna look at the comparison. So here before, like as I told you, you can do it for all the 6 years we prepared the data for you. I did it before, so we have, I think, if the, yeah, okay, great. I thought it's not gonna work because sometimes it doesn't save it. So now you see this is the same glacier with evolution in 2018. So you see that it has a different area. Also in 2019, great. You see it's like kind of bigger, but again, we cannot say that exactly. But oh, actually, there's no climate change, and it's actually gained more ice in 2 years. But no, it's just, well, a lot of conditions, a lot of other stuff. In 2020, I assume in 2020 there is no data. Yeah. Also, for example, if you're gonna look more precise, you'll see that in a data and play it yourself. You're gonna see that for some dates, for some years, there's gonna be not all 4 tiles which we chose, because, well, sometimes it's not just available there's no satellite picture, or maybe it was satellite picture but it was fully with cloud, so we couldn't extract data, and so on. So 2021 we see some, and 2022 I think, yeah, there's also no data exactly on the LH glacier. So yeah, now we know how to work with TIFF files. So it's a satellite images. Usually they're in TIFF, sometimes in other, but quite often in TIFF. And we know how to work with these raster files, how to perform different calculations, and, well, yeah, manipulate them. So now I'm gonna untag this. Oh no, actually I'm gonna just to know where is it. And now we're gonna move to the second like sub exercise of this big exercise, is to look at meteorological conditions. So basically what we're gonna see is, well, to like draw some conclusion, to have like comparison between what the weather was and how what was the meteo conditions, how they influenced the glacier itself. So for this, we're gonna work with 2 variables. It's gonna be air temperature on 2 meters from the ground, and also total precipitation, which, well, the temperature like influences, of course, like if it's gonna melt or not, even though it's this glacier is quite high, so the temperature there is different. I mean, the changes differently, and the total precipitation is basically how much this glacier could have accumulated snow, water, whatever, in whatever condition, whatever it falls. So for this we use this ERA 5 product, and now that's the time when we use the plugin I told you, which is called NetCDF to GIS. It's here. This is little icon with Copernicus Marine Service logo. Well, it's written how to download and how to install this plugin in a workshop, in a document version, but I'll still show you. So you have these plugins here tab. You click on it, you put manage and install plugins. And here you browse to your zip file. For example, it's this one for me. And as soon as it appears, like just a zip file, don't need to unzip it, whatever, you just click on install. It says, great, I'm good, I'm working. And then you can have this, I think you already will have icon. If you want, you just, well, save your project, close QGIS and like reopen it. So we open it, and I already added the our Era 5 product, but you can add it again by clicking on plus and browsing to whatever your data is at. And also you can, again, drag and drop like this. Might actually add it again. Great. I'll remove it. So here in this plugin, you basically can add all the NetCDF files here. You can see variables which are stored in this in this product, and here it's the name of not kind of variables, but it's more like dimension. So here it's like time, latitude, longitude. So basically that's the NetCDF thing, like it always has latitude, longitude, and time. And you can see some metadata, some options if reprojections, which you also can do later. So it's not like you need to think about it more right now. So what we're gonna do now is we're gonna map these two variables, which is temperature, and this is total precipitation, TP. So again, we have data for like 6 years. We're not gonna do that. We're gonna only look at the 2017 and, for example, 18, whatever. But I'm doing it for 1 year, and yeah, you can repeat for more. So I'm gonna right click on one of the variables and click on add layers of several variables. So this function allows you to choose only choose time frames you want for one variable, and it will automatically choose the same one for other variables or the closest one if the same one is not available. So here we have only one file, so we click on both because we need both variables. Next. So now you see we have two windows. Op. And I'm gonna just work with 2017. So you see, as I'm clicking on the temperature variable, like time frames, you see that for total precipitation, it also chooses the same one. Well, here the time is the same, so great. So for each year, we have actually 5 dates. That's actually mean air temperature 2 meters, like monthly mean. So we have like one monthly mean for January, February till May. So basically, we're gonna look at the meteorological conditions before this the pictures, like the satellite images which we used. So I'm gonna choose this. I'm gonna hold Shift and choose this 5. You see every other one has been chosen in auto precipitation. I put add and close, and it will add them both. Great. So, oh, that's actually yeah. So here, for example, if I do this just for you to see, yeah, I mean, here we see that the Era 5 resolution, don't remember exactly how much it is, I can check, but we see that probably it's like, I don't know, 5 kilometers, I don't know. So we see that the resolution is quite low. We have only like 1 pixel covering all our glacier, but overall we can just, again, it depends on different data and stuff. We can just see how it's like what's the evolution of the temperature and precipitation, and also the main thing is also how to see how to use these NetCDF files in QGIS, how to work with them, how to transform, and so on. So you see that we have our, oh, it's actually 2018. I guess I also added it. So yeah, we don't look at 2018. So here we see our evolution. Also, so you see how temperature, well, yeah, you see the scale. But first thing that we're gonna do, as we saw these clipped areas we had it per year, right? So like we looked like at the May, you know, like so at the end of the May, and here we have a mean for each each month before May, like from January to May. So what we're gonna do, we're gonna calculate the mean of the means. So mean over 5 from like 4 or 5 months. It's actually very convenient thing what you do in QGIS. And for this, you go and you choose cell statistics, I believe. Yes, okay. Cell statistics. So in a cell statistics, we can calculate actually different statistics, or one by one, I think, unfortunately. So here we choose mean because we just need a mean temperature. And for inputs layers, we're gonna choose, each date corresponding to 2017, 2017, 1, 2, 3. Okay, it's 5. Okay. Again, we can say we cannot or we cannot. Reference layer should be the same. Yeah, okay, great. Did I choose? Yeah, okay, great. We run and we have our output layer, which looks like this. Well, we can also adjust the styles of our layers, but we're gonna do it a bit later. So we're gonna do it. You can do it for the same thing for our years and stuff, and we will do the same for our. You know what? Let's rename it so we don't lose it. So it's T2. Wait, what it was 2017, right? And now we're gonna perform the same for our precipitation, but now we go to cell statistics, and we don't use mean, we use sum. So we just want to all the total precipitation. So how it was accumulated, because well, if they did accumulate, of course, there's some like it's not like they all stayed as a snow, of course, but we're gonna assume this. So as a reference layer, we choose total precipitation sum, and we choose total precipitation layers for 2017 also. Oh, 5. Okay, run. Great. We will also rename it. It's TP 2017 also. I'm gonna put them next to each other. And for the TP, we already can change our, make it more representable for us. For example, we actually will look at the original one, so 2017 for January, right click, we click on properties, do the symbology. So here we can choose how our color map and stuff looks like. So we will choose, I think, blues because, well, it's water. We choose equal interval and put only 5. I think 5 is more than enough. And, oh, sorry. And we will put, I don't know, I think this is gonna be too, well, for example, I'll put as a minimum, I don't know, 0 like this, for example, and yeah, max like this, for example. And yeah, the more water, whatever more precipitations, the darker it will be. I'll apply, okay. And then I can right click, go to styles, copy style, and like progress them to all our layers and also to our mean one or sum one base style. Oh, okay, so it was too much for this layer. As you can see, it's like oversaturated. So we can also double click and change it, I guess. I don't know. Did it change? No, I did not. Nice. Okay, well, I'll see. Yeah, okay. For example, this is our precipitation per month. Yeah, okay, it's oversaturated. You see, I should have done differently. But well, you see the evolution. So far, it's very bad evolution. I'll check if how I'll adjust it. So, but let's look at our temperature. And first, if we look at, wait, where is it? Okay, yeah, at our plugin, we see that it's actually in Kelvin, which is not very like representative for us. So what we're gonna do, we're gonna switch it to Celsius, which is more understandable for us. And for this, we go to Toolbox again, and we go to Raster Calculator, and I don't remember where is it. So Raster Calculator, I think it's this one. Probably. No, it's this one. There are two raster calculators. Yeah, this one. Yep. So here I'll paste expression, which I already have. Tick. So I just to calculate, but I have different name of my mean one, so I'll do it like this. Let me check if I really have it. Oh. Yeah, it looks like this. Okay. And what else? I think it's good. I need a reference layer. Well, it's gonna be TM. Okay. And output CRS. This is just a project one. And then I run. Great. So now the output is in Celsius. Well, yeah, before, because you saw it like 280 degrees, it's not what we see. So yeah, and this output I can change. It's not single band, it's single offset the color, same equal interval 5. Yeah, I don't know what's mean, -4 and max is like 12. Should be okay. And for example, wait, we use spectral but invert. Okay, so here we have our mean temperature in the 5 months of 2017, first months. So you can see that's like here it's well, in the mountains it's colder. Yeah, makes sense. Also like in closer to the sea it's warmer, but we also see that it's like 12 degrees max or something like this. So basically that's it. And like this, we can compare it with other layers. Like I will only look at the temperature for now. Like we have wait, yeah, so like this is mean temperature in 2017. This is in 18, 19, 20. Well, it's quite warmer, much warmer. 21 again, okay, 22, like this. And also I already prepared the same for the total precipitation, which is 17. Let me just click it like this. And you see that sometimes, well, it's more, it's less. Well, you don't see really like to draw a really conclusion like, okay, that was more, that was less. Maybe a more in-depth study should be done. But overall, to understand how you can use products from a WEkEO platform, how you can work with them in QGIS and what to do with them and compare. That's it. And well, yeah, we learned today how to use products which are satellite images in TIFF, so they're raster layers, and also how to work with vector layers, also how to transform them between vector and raster layers, and how to work with netcdf files, which are like, yeah, most of the data in at the WEkEO platform is in TIFF format as satellite images or as netcdf files. So that's it. I hope I didn't take too much time because I didn't really look at it. So
No,
yeah,
it
if you
was
have questions.
perfect on time. Thank you,
Great.
Daria. We do have some questions for you. If you could stop sharing, perfect.
Yep. Okay.
Great. So the first one is a bit of a more general question. In your opinion, what do you experience as the most challenging part when using satellite data for scientific investigations?
Well, I
quite
think
general here.
yeah, I think the most challenging part it's that well, satellites have their constraints, like they have resolution constraints. Sometimes when you need to look at very small small-scale data satellites, with especially the free satellite, like available for public. They don't have very good resolution, and well, and the satellites with high resolution images, it's quite expensive. Also, of course, another constraint is time. So in terms of time, sometimes you cannot find the time frames, the dates you really need for that, because it just wasn't available, or I don't know, satellite wasn't passing there, or something happened, or whatever. And also, like, well, depending, but if it's yeah, sometimes like if it's a set like Sentinel-2, for example, images, like there are clouds or whatever, like, so there's always can also like can be, yes, it's optical image, it's also shadows on a picture also can, well, depends on what you're doing, but for example, for some image processing, even shadows of a cloud can actually be a problem for your scientific investigation.
Mm-hmm. In terms of the data you used here, you mentioned Area 5. Do you think in terms of resolution it was good
Yeah,
enough
I mean,
for
yeah,
this study,
here
or?
for this study, yeah, we can see that, for example, I mean, you don't see my screen anymore, but we saw that for the Area 5 data, we had only like one big pixel which covers not only the glacier of interest, but like a huge area around, which, yeah, not really represents you, but at the same time, like, as it's a valley, I mean, the glacier usually lays in the valley because it carves the valley by moving, and we might kind of the same altitude, not big like drops. We can assume that it's the same, like temperature, but sometimes at this
Mhm.
pixel there also can be a mountain peak which is like, I don't know, 2,000 meters higher than the valley, which of course not going to be the same temperature. So yeah, here it's it depends of course on the study, but here, yeah, it was maybe a bit not too precise in terms of resolution.
Mm-hmm. Okay, thank you. And so the next one, how do you verify your data analysis results? I'm not sure if they mean
Yeah,
like the
that's
statistics you did, or.
yeah, that's the question. Like, yeah, as I said, like for example, we saw that for this persistent snow area, which we looked at. You saw that it doesn't detect exactly how glacier looks like at a specific time, because, well, as I said, it detects yeah, like it doesn't see some snow because it's dirty, for example. That's all. Like dirty snow is already not reflecting, not showing the same values of pixels. And so yeah, like for this you need to have some additional like backup, or like some other source of information, other tools which you can combine and make your study like more reliable in that terms. Or again, like if you do it for yourself just to like learn how to use the data, how to do the processing and stuff, of course you might already maybe found some reliable source of information which says, okay, this is was the area like of our glacier at that time, and you just compare how did you get like what you get. But I guess it's always comparison and always like compilation of different tools and methods.
Okay. And will this method work for other regions, such as in the poles?
Yes, yes, it will. The only thing is that, for example, for poles, I'm not sure that this exact product, like this Copernicus high resolution persistent snow area thing, I don't think it's available for poles, because I think it's been only for like European region. But for poles, there are other products which include also persistent snow area, or like there's also another there's another variable which also like shows the cover, like snow cover or ice cover. So basically, yes, you basically what is good about tutorials, when we do tutorials, like in this tutorial you can change the subject, you can change the data, you can change whatever, but you still know how to work with them in like QGIS or like in Jupyter Notebook, like it will be shown later. So you just apply
Exactly.
it to any subject,
To any
any
topic.
region and data. Yeah.
Exactly. The idea of these tutorials, of course, it's to bring interesting topics, but also mainly to teach you how to use these tools. And the next one. So what are the uncertainties of this analysis? I think you covered that one maybe already.
Yeah, it's like,
Um,
again, like we don't know, we need to compare, and yeah, that's it.
mhm.
Also, like very quickly, like if you really want to have like want to do more precise, yeah, like study, you can try to do the study not for like, for example, I used like mean temperature, for example, and then I did mean over mean, or like I used only one month for satellite images. You can try to like have as many images as possible to really like see how it
More data,
fluctuates through
yeah.
like from data. Of course, it's going to be more like meticulous. It's going to take more time, but
But you
yeah. And
you
it
maybe
also
increase the chances of accuracy.
yeah, but it also depends, like if this data is available, because again, like
Mm.
satellite didn't pass at this time, or it passed but didn't capture it, whatever.
Yeah. And one question about the NetCDF plugin: is it just for Era 5 data, or is it also valid for any NetCDF files?
It is valid for any NetCDF files. So any NetCDF files that you have on the WEkEO platform or some other platforms, like, because well, NetCDF is a file format, so it's more or less like structured. Sometimes you can find NetCDF files which are a bit broken, kinda like they have data not specifically like stored, like, or whatever. But as yeah, you can still try with this plugin, or well, you can always try it with built-in function in QGIS. It actually might open if like the file was very like not really nested variables, but just like a list of variables. It might understand it like properly.
Mm-hmm. Okay, yeah, we in the tutorial you will find the link to the NetCDF plugin.
Plugin.
Yeah, so you can download it. And okay, this next one, I don't know if you know about it, but are there scripts in R to do that?
About R, I cannot say. I don't know, but I wouldn't be surprised if yes. I mean, now you can write a code for anything in this world everywhere. So
yeah, I'm sure
well,
if
we
you
don't have it, yeah, but
look online, yes, we're not focusing on that on this workshop, but maybe we should. Is there any way to distinguish between ice and cloud from satellite image?
yes, I think I don't. I mean, I'm not the one who processes satellite images to say is it snow or cloud, but yes, I think that they have different at some point, like, because well, each pixel, like, it comprises of several like it has its own value, right? And it like comprises of different like, how to say, like parts. Also, you can have like to calculate, you use different, like to calculate ice cover or like vegetation cover or whatever, you use specific indexes which usually use different spectral bands of the same image, like different combination of these bands. And in these bands, for example, in like one band is like, I don't know, vegetation is more black and the water is white, or something like this. So I think ice and clouds are different. Yes, I don't know how much is it, like, can we really say it, but also, like, if you see an image of like, well, sometimes clouds are very like obvious because we have like some I don't know, some little puffy cloud shape, which you're like, okay, well, but it's definitely not
Not
I don't
ice.
know, not ice or not a city or something,
Doesn't
like,
look as
so
fluffy.
yeah, exactly.
Yeah.
So
Okay. And a last question: could multiple data sets be used to extract valuable information? Is an example available somewhere?
could multiple data sets be used to extract? If by data set you mean like different NetCDF files,
I guess
then
so.
yes, yeah, because in the plugin you can insert like as many NetCDF files as you wish. And again, as I said, there's this feature in a plugin. When you add layers, you can add layers for several variables from several NetCDF files. So you don't need to go to NetCDF file, choose a variable, choose the data frames and the time frames and build them, like plot them every time. You can choose all the variables like you want to plot from different NetCDF files, choose one time frame for one time variable, and it will choose again like the same time frame or the closest one from other ones. So it's much faster. Like, I mean, it's not like it's some very important thing, but it just saves time, because if you need to process a lot of files, a lot of data,
Yeah,
it
the
takes time.
different
So
times.
yeah.
Yeah, that can take a while. Okay, I think that's all for you. Thank you very much
Okay,
for your
thank you.
presentation. That was very nice. And now we'll have a short break. Maybe let's do 10 minutes, and we will be back at 11:25. I'll see you in 10 minutes. Welcome back, everyone. I hope you're still around. We have one more tutorial for you. So now from the Alps, we are going to the Antarctic with Alexandre Omeran. He's going to show you how to study the dynamics of the Antarctic ice shelf. Floor is yours, Alexandre. Hi.
Hi. So yes, hello everyone. I'm Alexandre Omeran from Noveltis. So yes, today I will show you a Python tutorial to monitor the cryosphere. Let me just figure out how to share my screen and we will start. Okay. So I think you should be able to see it right now. Is it okay?
Yes, perfect.
Yes, perfect. Okay, so in this training, I will show you a few things that you can do to process data over for cryosphere studies. And our main focus will be on the Antarctic. So I think we've already introduced the subject about the importance of monitoring cryosphere, which is mainly directly linked to the rise of the sea level. There are many ways to monitor the cryosphere, to measure the changes in the mass of ice over the Antarctic or Greenland or other glaciers. Our main focus in this training will be gravimetric measurements for ice mass balance. So that's what we're going to work with in this training. So we're working with Python. So when you do this training by yourselves, make sure to activate the mini WEkEO lab environment here. So you just have to click, and if you're logged in with your WEkEO account, you should be able to find it. So it has all the necessary Python libraries pre-installed. So with this, you should be able to execute the whole notebook perfectly. So here are the fundamental packages used in this training, many of which are quite common in Python. So NumPy is widely used in Python to process data arrays. Xarray will be the main library used to open the netCDFs that we are going to work with. And those two libraries are meant for plotting the data to visualize our calculations and measurements. And finally, this is dedicated to the manipulation of geography datasets. So you will see later how this is used. So with this first cell, we import everything that we need. So you can recognize here the different libraries that I've mentioned before. And now I'm going to show you a little bit the product that we're going to use in this dataset. So as I mentioned before, this is a gravimetric measurement product done with two satellites. So the Gravity Recovery and Climate Experiment is called GRACE, and its follow-on mission, so the next satellite that is sent after the end of this mission, the GRACE follow-on mission. So they've been operating for nearly 20 years and have been measuring the Earth's gravity field. And this data has been exploited to derive mass changes over Greenland and Antarctica. So the finally for the product on WEkEO is Greenland, but of course we're going to use the Antarctic data. So we're going to work with time series. And of course, if you want to know more about the product, you can either go to the WEkEO dedicated page. So it will redirect you to the data viewer and show you more about the product. And if you want to have even more documentation, there is the original dedicated Copernicus page with all the relevant documentation that we'll need if you want to find out more about the product. So here's a brief section about how to download data in WEkEO. So in a simple way, one thing that you need in Python to download through a Python is the point HDRC file. So WEkEO provides many articles to walk you through the different steps to writing this. And with this cell gives you a simple way of doing it if it's not already done. So if you execute it, if you don't have already the necessary file, it will just ask you your credentials, and those credentials will be written inside the files, and then this file will be used to access the WEkEO data catalog, and we allow you to download the products. So I do already have this file in my WEkEO repository, so it didn't ask me my credentials. So I'll just move on to the next cell. So yes, after you've created this, you need to write your data requests in a JSON file. So for example, if you work with the WEkEO data viewer, for example, and okay, so I probably just describe it on the notebook. So when you select data on the WEkEO data viewer that we saw here, at this downloading step, you can tell it to show the API request, and it will show you your request as written in the JSON file. So, for example, for the gravimetric data, this is what it will look like. So you have the attribute dataset ID, which is the identifier for the dataset. So as we can see here, it's indeed the ice sheet mass balance. And here's a pretty simple request because I'm asking for all the variables in a zip format. But for example, with other datasets, you can, for example, specify which date range you want to select, which geographic range you want to select with latitude and longitude boundaries. But in our case, it's pretty simple. So with this cell, so I'm pointing to this JSON file here. And this cell, once executed, shows me the request that I've just shown you here, only in a more compressed style. And once that's done, once your request is read, this cell should be used to download the data in your data directory. So as I've already downloaded the data, so to save time, of course, I'm not going to do this right now. But if you do the training by yourselves, all you'll have to do is to uncomment all those lines, so remove those few hashtags here and execute the cell. Okay. So now we have our gravimetric mass balance dataset downloaded. And we are now going to open it for the first time and see what it looks like. So now as you can see, we're using the X-ray library that I've mentioned at the beginning of the training to open the netcdf file. And here we print the dataset and see what we have here. So as you can see, there are many variables, 81. So when you click on you can uncover everything and see what variables you have. So we have many things. First of all, we can see that we have variables starting with ent and some variables starting with JR. So of course, JR is meant for Greenland and ent is meant for Antarctica. So we'll be interested in the Antarctica variables. So if we just look at, for example, this variable, we can show its main attributes. So here is the total Antarctic ice sheet gravimetric mass balance in gigatons. And so this is a total. And as we can see, we can deduce that the other variables are like subdivisions of this total, because here it's the ice mass balance on the West Antarctica region, here on the East Antarctican region, here on the Antarctic Peninsula. And here are 27 other subdivisions of the Antarctic continent. So we'll get into this in more detail later. So as we can see here, all those variables are only functions of time. So we're working with time series. And here at the top, we have indeed our time variable. And we have another variable here that is not linked to time. It will be important later in the training. So we are saving that for later. If we look at what it's called is the basin definition. We look at that in the next section. So this is what our raw dataset looks like. And so there are a few things that we are not satisfied with at first. First, so we have this coordinates attribute here, which should have, usually NetCDF datasets have, for example, coordinates like such as time, longitude, latitudes, referred to as coordinates, and which makes it very easy to process and work with the dataset afterwards to make other analyses and calculations. So with this dataset, we don't have that, for example. Another thing that is not shown here, but that is also a problem, is that the temporal resolution is irregular. So ideally, we should have one value per month separated by exactly 1 month every time. So with the dataset, we have a few holes in the data and some irregular time steps. So as a first step, we're just going to reprocess the raw dataset to have something that is easier to work with. So that's what I'll do here. I'll just regenerate the dataset while defining time as coordinates. This is the main concern. And here I just resample the dataset to have exactly one value per month. So this is used by using the resample function of the XRA library. So we are reprocessing the whole dataset, so it should take a few seconds to execute. Okay, it's done. And now we have the new dataset that we're going to work with. So now we can see that we have a time coordinate, which will be very convenient in the next sections. We have less variables because I've only kept the variables related to Antarctic. So we have no more variables for Greenland. So the dataset is a little bit lighter in terms of memory usage. And now we can start manipulating this dataset. So in this section, I'm just going to show you a few common manipulations of time series. Particularly how to select value and how to subset the dataset. First, we can take a look at the time coordinates in the dataset. So now, as you can see, we have one value per month here. And every time the time coordinate is centered at the end of each month, so 30th of April, 31st of May, and so on. So if you want to select an exact date in the dataset, you can use the cell function. For example, here, I want to select the month of June 2014. And here, as you can see, only the value for June 2014 will be in the outputs with all the different values for each variables. So now, if you don't know the exact date in the dataset, because of course, if here I select a date that is not in the dataset, it will return an error. So if I don't know the exact date, but I want to have the nearest date in a dataset, I can specify this argument in the cell function. So for example, here I want to select the 5th of June 2014. So this date is not in the dataset, but with this argument, it will yield the closest value to this date. And here, as you can see, the closest value to the 5th of June is the 31st of May, 6 days before. And same thing, all the different variables are still represented. Another way to select data is the iCell function. So here it's used to select data from its index. So if I specify, for example, 3 here, so as indexes start with 0, this will return the 4th value in the dataset. So here it's the 31st of July. And if we remember, the dataset started in April, so this is consistent. And one of the most useful is to select a date range in the dataset. So for example, here I can specify a range of dates and it will select all the data that is between these two dates. So for example, here I'm selecting the first semester of 2015. And we have our 6 months here represented with all our variables. Okay, so now we're going to perform a simple plot of data. So we will take a look at the mass balance, at the total mass balance of the Antarctic ice sheet. So we are computing the values here. The error suffix is actually the uncertainty on the measurements. So we're going to plot that too to have to see the range of uncertainty over the time period we're studying. And here it's all those lines are about the plot parameters. And as we could have expected here, we clearly see that there is a downward trend in the mass balance of the Antarctic over the last 20 years. So this was something to be expected. And for example, we can also see that there is a seasonal pattern in the mass change. So in the next section, we're going to smooth that out to have only the yearly pattern of the mass change. So this is a total mass balance. What we're going to look at is, as we could see, there is a subdivision in the data. So we're going to look in more detail how the mass balance is geographically distributed. So as I said before, we are going to use yearly value to smooth out the seasonal pattern of the mass change. And we will only be taking 2003 to 2020 because those are in only years that are full. Because as we remember, the dataset started in April 2002 and ended in February 2021. So for yearly values, we will only be keeping the full years. And we're going to plot a first subdivision of the ice mass change. So we're going to look at the east, the west, and the Antarctic Peninsula. And this is already quite interesting to see that the ice mass change behaves a lot more differently depending on the geographical area. So we can see that the East Antarctic has actually an accumulation phenomenon. So the mass of ice is increasing since has been increasing for the last 20 years. And both the West and the Peninsula have decreasing trends. However, on the Peninsula, it's less. It's decreasing slower than the West Antarctic. So this is a first interesting observation. And now what we're going to do is we're going to look at the 27 drainage basins of the Antarctic that we could see in our data. So as you remember, now we will be looking at the 27 here different basins. And as we remember, at the very sorry, I'm going a little bit too fast here. So now we're going to subdivide even more the Antarctic mass change dataset in order to look at each basin individually. So if we have another look at the initial dataset, I told you that there was one variable that was not related to time. So going back to the top here, and this is this one, the end basin variable, which looks quite strange in terms of coordinates here. So if we look at the characteristics of the variable, of its attributes, we can see that it's actually the basin definitions of this variable is the geographical definitions of the 27 basins that we have seen before. So here is the reference of where those definitions come from. So you can explore it if you want. And so it consists in a table with 3 columns with latitude, longitude, and the corresponding basin number. So going back to where we were, this is indeed what we have. This looks like latitudes, longitudes, and a number that goes from 1 at the beginning to 27 at the end. So this seems to be consistent with the attributes shown in the initial dataset. So actually, those latitude and longitude points are the contours of the Antarctic regions that have been defined in this dataset. So what we're going to do is that we will take those contour points and draw polygons with them. So we will just, compute the corresponding polygons for each basin. And this is what we do in this cell. So I'm going to start the execution because it takes us some time to execute. So it's a little bit complicated and you don't necessarily have to exactly understand everything, but this is the first time that we were going to use GeoPandas. So now we're going to use geometrical datasets. Basically, it's just about computing each point thanks to the latitude and longitude coordinates that are provided here. So the points are separated in 27 groups, and each groups has many points, and with a function from GeoPandas, we just gather those points into a single polygon. So we'll have a much lighter data set in the end of at the end of this execution. Okay, it's finished executing, so we can continue. So as I said, the result of this execution is a geographical data frame. So if I upload the first 5 lines here, we can see that we have a table with the basin, each basin number. So if I just plot the full data set so you can see better what I mean. Oh, okay. So we have a table with 27 lines and a geometry column that defines the polygon for each sub-region of the Antarctic. And here is the center point of every polygon, which will be useful for annotation. So here I've only described the data set. So now what will be interesting will be to see on the map what it looks like, because that's the point of a geographical data set. And that's what we'll be doing right now. So all those lines are for plotting the map over the Antarctic. And with this line, we plot our geographical data set. So it's a very simple plot. We're just plotting actually the contours of the region that were defined in the gravimetrical balance dataset. So maps take a little longer to plot. But this was the whole point of these sections, to compute the polygons defined in the GRACE dataset. So we have our 27 subregions of the Antarctic, and this map will be our baseline for the next analysis, the next sections. So here, for example, so in the next section, we will compute the trends, the mass change trends for each basin individually. So for example, here, I'm showing you a simple way to compute a trend in Python. So you can use the polyfit function with NumPy. And this yields this dashed line here with a slope and an intercept. So what is interesting to us here is the slope. So apparently for basin number 21, over the last 20 years, it has a linear trend of approximately 57 less gigatons per year. So basin number 21, if we look at the map, it was this one, for example. So for basin 21, the mass is decreasing pretty fast. That's what we can say here. And so we will do the same thing for each of the basins. So here we apply the polyfit functions for the 27 basins. So we do a loop over the total number of basins. And now we just add the list of trends to the geographical dataset. And now we have the same dataset as before, only we have one more column here, which is the yearly rate of mass change, or the linear trend. So this is in gigatons per year. And now that we have that, we can plot the same dataset with while and visualizing at the same time the trends on the map. So basically, I'm doing almost exactly the same plot, only this time I'm adding the yearly change rate as in order, I'm using this to color the polygons. So this is our result. And so the variability in, well, the geographical distribution of the rate of mass change is clearly visible here. So we can see that indeed in the West Antarctica here and on the peninsula, we see again the decreasing trends that we had seen at the beginning of the study. And there is a major part in East Antarctica that is actually has an increasing mass of ice, apart from a few basins here, but they're not decreasing as fast as West Antarctica, for example, which is decreasing at the dramatic rate, actually. And now to go further, we are going to look at the, well, so sort of the second degree derivative of the mass change, so the rate acceleration of the mass change. So we're just going to compute the gradient of the mass change time series and do, once again, the linear trend for all the basins to see if we have a different results, or if we can draw more subtle conclusions from this gravimetric data. So once again, we perform the same calculation. We add a new column, so the yearly mass change acceleration, to our geographical data set. And we use it again to plot the acceleration on the map. Okay, so the colors have changed a little bit. If we remember, those were blue, so we had an increasing mass rate. But as we can see here, although the mass is increasing, it seems to be, the rate of increasing seems to be slowing down a bit over the last years. So this is, for example, one nuance that we can give to the first observation that we had made. So here I'm just visualizing side by side the two plots that we have just made before. So we have this for the West Antarctica. We can see that it's already decreasing at a dramatic rate, and it seems to be decreasing faster and faster over the years. For example, over the peninsula, we can see that it is indeed decreasing, but the decreasing rate seems to be slowing down because the acceleration is positive. So yes, this gives a more in-depth analysis of the dynamics of the mass change in Antarctica. So indeed, the ice shelf in these regions is well, crucial to monitor. So in this section, this section is about making a little animation of the evolution of the ice sheet of the Antarctic. So I'm not going to execute everything because it takes some time. So here we're just resampling every 2 years. So to make this animation, what we should do is generate one plot like this every year or every 2 years here, because otherwise it takes too much time and we have too many images to process. So every plot is saved as an image in the data directory. So here it will be, I've decided to save them here. And all these images here are computed to make a GIF image. So I'm not going to execute this because generating all the images and saving them takes some time. So I'm just going to show you the GIF images, the animation. And so with Python, you can perform animation like this to show the evolution with time. So this is very simplified, but this is something that is well, quite funny to do actually. And it does show the evolution pretty well. So here we take our plot of the total Antarctic ice sheet, and here we can see the subdivision and well, the trends they follow over time very very visually. So this is a nice figure to plot regardless of what analysis you do. Okay, one final thing we will do in this training is to see the correlation with sea level evolution. So as we know, the melting of the ice sheets is a major driver for the rising of the sea levels. So here I'm quickly using another product from the WEkEO catalog, which is so a sea surface height dataset. So once again, it is available on the WEkEO data viewer. So if you want to see more about these datasets, do not hesitate to visit the dedicated page or on the Copernicus Marine Service dedicated page. So you have all the relevant documentation here. So our dataset goes from 1993 to 2022. So it covers the time period that we've been studying with the gravimetric dataset. So same thing here. This is a data request for WEkEO. So here it's a little more elaborate. As I mentioned before, here I've selected a start and end date to retrieve the dataset, and here I've selected the variables that I wanted to have. So same thing here. So which is a little bit different with this dataset is that if you download it through WEkEO, you will have many datasets that will be downloaded here. I think you can see on the left of my screen. So we have monthly values, and WEkEO will give you one file per month. So basically, if I check how many files are in this directory, we have 240 files, which is well, 2 years of monthly data. So what we can do to work with this is that with Xarray, you can open multiple datasets at once. So here I've listed all the file names in this directory, and I can open all of them at once. So I hope it won't take too much time to open, but it should be okay. It's still executing. Hopefully it will be done soon. Okay. So here I've opened everything. We can see that we have our 240 time steps. But as we can see here in the variables, well, the values are quite strange. We can see that the variables are separated into several chunks, and it's not convenient to work with. And this is because we have opened several different files. So what we can do to simplify this is to export this multi data set into a single netcdf file. So this is what this line does. And then we can close this data set. So I'm exporting it to this sea-level data 2002-2022.nc. So this is exported here. And now we can reopen it, our full data set. And now it is a regular netcdf dataset that we can easily work with. So there are a few things to change the dataset before we work with it. So we can see that here the longitudes go from 0 to 360 degrees. It's much more convenient to have the longitudes going from -180 degrees to 180 degrees. So with this cell, we will just perform this conversion. And we can do a first plot of our data. So here you can see that it's a little more elaborate than the simple time series that we had before. So we still have a time coordinate. And this time we have latitudes and longitudes because it is a spatial data set. And we'll be looking at the SLA, which is a sea level anomaly. So yes, that's what we're going to look at. So it's the anomaly with regards to I think it's a 20 years mean. I think it's from 1993 to 2013. I think I should check the documentation to make sure. Right, to select, for example, here January 2005, working with the sea level anomaly. So we can see that sea level is not equally distributed. And what we're going to do is that we're going to look at what happens near the south of the ocean, so near the Antarctic, and see how it correlates with the mass change of ice in the Antarctic. So here I'm using the cell function, but this time with latitude and time to select only the 20 years of the Antarctic and the southern latitudes. So we have the same data set, only this time we can see that the latitudes are in the range that we have specified here. And our longitude are from 180 to from -180 to 180. So we are going fine. And to calculate the correlation, we're going to simply use the Pearson coefficient. So it's a coefficient that measures the correlation between two data sets, and the coefficient goes from -1 to 1. So value 1 implies that there is a perfect linear relationship, and the value of -1 is that there is an inverse linear relationship, and the value close to 0 indicates that there is no correlation at all. So we're going to use that first on the
I think we are losing Alexandre.
okay, it takes more time than expected to execute, but it should be okay. Okay, but I did not expect this to to be this slow. Okay. Oh, okay, it worked. Okay, so here I've plotted to have a visual experience of it. So the Antarctic mass change in gigatons versus the sea level anomaly in meters. Here the Pearson's correlation is minus 0.727. So which is a rather strong inverse correlation. And we can see here that the low values of mass balance are mainly correspond to the high value of sea level anomalies, which is consistent with what we should expect, because if the ice melts, it is logical that the amount of water that is goes into the ocean makes the sea level rise. So this is quite consistent, apart from a few outliers here and there, but this is what we should expect. And now we're going to have a little more detailed analysis by looking at the spatial distribution of this correlation, just sort of like what we did with the Antarctic. So here we don't have specific drainage basins like with the Antarctic mass balance dataset. So we're simply going to draw 18 simple sectors around the continent. So I'm basically drawing polygons out of the blue, and you will see when I plot the map how they're defined. But here I've plotted many polygons over my dataset and computed the trend in sea level rise for each one of them. And if you plot them on the map, this is what we get. So here we can see that over the major part of the surroundings of Antarctica, the sea levels have actually been rising over the last 20 years, which is consistent. But in this particular area near the West Antarctic, there is an inverse phenomenon where the sea level is actually decreasing, which is quite astonishing at first. But this is actually something that is known, because the rise in the sea levels is actually not equally distributed. Actually, so this comes from a gravitational pull that is linked to the melting of the ice and the readjustment of the solid Earth under the ice, which is a phenomenon that can upset the measurements of ice balance, especially with gravimetric measurements. And yes, actually, the gravimetric pull, and also another phenomenon is the oceanic circulation, is something that changes the spatial distribution of the sea level rise. For example, the melting of the Antarctic, because may have not necessarily a big impact near Antarctica, but may have a bigger impact, for example, in North America. So this is a phenomenon that is very complex and not necessarily easy to understand. But this is what makes monitoring, on the one hand, well, ice mass change, and on the other hand, sea level dynamics, very important to monitor. So we're reaching the end of the training. So I hope that with those chapters, you have learned to well, conveniently manipulate data with Python. So I hope you enjoyed it. And now, if you have any question, do not hesitate to ask me anything.
Thank you, Alexandre. It was very nice. We do have one question
Okay.
for you. So I can read it to you. Oh yeah, I can see it on screen. So do you know if there is any data on WEkEO related to Greenland? I think the similar data that you have used
Yes,
for
the
Antarctic.
dataset I've used has actually data for Greenland also. So
That
I
must
think
be
if you
visible
refer to
directly.
the first sections of the notebook, you will see that when we first take a look at the initial dataset before we process it, there are many variables that are related to Greenland with the same pattern of subdivision in many basins, etc. So you can actually perform almost the same analysis with Greenland with the same dataset that I've used in this training.
Okay, yeah, perfect. That was all the questions we had for you. I think either people didn't have time to maybe take a look at it at your tutorial, but they will be able to. You will be able to rewatch Alexandre's tutorial, so you can follow along, and maybe then you will have questions. But I hope you enjoyed Alexandre and also Dario's presentations. All the resources will be sent to you on an email. And thank you very much to everyone, Alexandre,
Thank you.
and Daria. So we get to the end of this workshop. Hope you enjoyed it. And I see you in our next workshops. Bye-bye.
Bye-bye.
Oh, just one last thing I forgot. So if you could spend just a few minutes, we will be leaving a survey online on Slido as well. You can access it just to leave your opinion, have a few questions that would be really helpful to us. Thank you.